3. What's that, Josh? Yeah. Um, Continue with chapter 3, and I have your exams. I'll return them at the end of class. All right. Let's see. So we're talking about electrical energy and power. As I said, chapter 3 is really just sort of a precursor or a prequel to what we get into in chapter 4, sort of laying down some of the basic ideas. So for electrical energy and power, batteries convert chemical to electrical energy. And then that's converted to, mechanical energy or thermal energy. And some of you as chemists might be involved in designing batteries because it is very much a chemical process that you store the energy in these chemical bonds, and then by some process you release that, moving electrons around. In fact, who was it? Oh, Rebecca Adams a few weeks ago, she talked about solar cells and the use of solar cells and optimizing the transfer of those electrons. So there's a lot of cool chemistry that goes on with that. But we'll look at in terms of the electrical energy of batteries. It's useful to be able to describe the amount of energy that's provided by a circuit. So if you remember, we had this some time ago that our change in potential energy is equal to Q times delta V. Sometimes we describe this as work, or if you recall, our potential is energy per charge. It's all wrapped up in that basic idea that a potential is an energy per unit charge. And so this is just a sort of a rearranging of that relationship, that our change in potential energy is equal to Q times delta V. Now, if we're thinking about power, as you know from last semester, that power is energy over time. Y'all recall that? It was like the work chapter that we did where we had to find the power expended by a force in a certain amount of time. We just take the work that's done by that force and divide by the time. You remember, sort of, kind of, power? Yeah. And since the current, which we've already defined as Q divided by T, if we take this energy and then divide it by time, that's an energy, so energy over time, we would get Q V over T. But then notice here that this Q over T is our current, and so then we get the expression for power, which is our voltage times Q over T, which is I. So that's our expression for power. It applies to any electrical device, and the unit of the power is the watt. Remember with watts that 1 watt, when we abbreviate it, it's capital W. So this is the W that you see on the end of your light bulb. It gives the power rating of your light bulbs or whatever electrical device you have. It's equal to 1 joule per second. You can also think of this as being 1 volt per amp. All right, that just comes from our power equation. Or excuse me, not 1 volt per amp, 1 volt amp. Don't worry about that. We'll just stick with the basic SI units of joule per second. All right. Sometimes, and we'll see, it'll be useful to rewrite this equation. These rewritings of the equation on your equation sheet, so don't worry about memorizing them, but just know that they're there, because we'll see later when we do the concept test that sometimes we'll need to look at the power in different ways. So we have P equals VI. That's our basic expression for power, and electricians use this a lot to figure out when they're designing a circuit, how much current will a particular device draw? How much current will a particular device use if it operates at a certain voltage? Especially like home electricians, because they know everything operates at 120. If you have a 1,000-watt device, then you can calculate the current that that device is going to be using. But anyway, that's our basic expression. Now we can make some substitutions. Since we know that V is equal to IR, we can plug that in, and we get P equals I squared R. I just substituted IR in for V. And then also, since I know that I is equal to V over R, I can substitute this in there, and I get power is equal to V squared over R. The reason that's important, and you might not see it now, but you'll see it later, and I'll refer back to it. The reason that's important is that sometimes if I'm looking at a circuit, I'll have one thing that's held constant, and then I change something else, and then I want to know how something else changes. So for example here, let's say that my resistance is held constant. If I increase the power, I increase the current. Whereas here, if I increase the power, I increase the voltage, and I increase the current. The resistance is being held constant, but both of these change. We'll see why that's important later. I just want to point that out. Don't sweat it right now if you don't understand what I'm talking about, because later we'll see some questions and it'll be more clear. Don't bother memorizing those. Those are on your equation sheet, but just know that they're there. Let's see, these are just some MCAT questions. They have more complicated MCAT questions on the MCAT, but I just sort of pulled some of these from a practice test. So let's just look at some of these basic ideas about resistance and current. You could see some of these like in your multiple choice problems. I have a current of 1 amp. It flows through a circuit for 5 seconds. I want to know how much charge Q has flowed. So my basic definition for current is Q over T. So if I want to know the charge, it's equal to the current times the time. That's 1 amp times 5 seconds. Remember, our amp is 1 coulomb per second. When I have an amp of current, that means that every second I have a coulomb of charge moving through that circuit. So it's a coulomb per second times 5 seconds. So I get 5 coulombs. Notice the seconds cancel. Also notice that your time has to be in SI units, that if it's in minutes or hours or whatever, you have to convert that. I think that comes up in your homework. R for 2 identically shaped conductors is in the ratio of 1 to 2. That means that if I were to do R1 over R2, it would be 1 over 2. The ratio is 1/2. I don't know if I have a couple pre-meds in here, but regardless whether you're doing pre-med or grad school or whatever, standardized tests, they really like to think about ratios, and you'll often see ratios on these standardized tests. So it's useful to just think about how things relate to one another in this way, and just get used to dealing with ratios and fractions in this way. So here, if I have 2 identically shaped conductors in a ratio of 1 to 2, the resistivities must be in what ratio? Well, you have several options, right? It could be their resistivities, that is rho 1 over rho 2. It could be A, 1. It could be B, 1/2. It could be C, 1/4. It could be D, 2. Or it could be E, 4. That rho 1 could be bigger or smaller than rho 2. Or it could be by a factor of 2 or by a factor of 4. Let's try this. Tell me, what is the resistivity of rho 1 to rho 2, that ratio? Or we could rewrite it as rho 1, rho 2, and then we'd write these like this: 1 to 1, 1 to 2, 1 to 4, 2 to 1, or 4 to 1. Those are identical expressions. What is the relationship of rho 1 to rho 2, the ratio? All right, let's stop at 105. 105. Okay, that's good. B is right. It's a 1 to 2 ratio, or a 1/2 ratio. We know this because our resistance is equal to rho, rho L over A. That means that the resistance is proportional to the resistivity, directly proportional. So whatever ratio I have of rho 1 to rho 2, I'll also have, or excuse me, the R1 to R2 ratio will also be rho 1 to rho 2. If you want to think about this in a slightly different way, you could take the two equations, R1 equals rho 1 L1 over A1. R2 equals rho 1, or excuse me, rho 2 L2 over A2. And then you can divide the two equations, and that would give you R1 to R2. And notice when I do that I get some things to cancel out. The L's cancel because we assume those are constant. The areas cancel, so I assume those are constant. And I'm left with rho 1 to rho 2. So the two ratios are the same. However, if I was looking at something else, like say the areas, it would be swapped because there's an inverse relationship. Or if I had a quantity that was squared, then it would either be this answer or this answer. This answer is a direct relationship, or this answer is a inverse relationship. Yeah, y'all should have done those things in high school, but it's good to jog your memory on those because we don't often think about ratios in that way, but they come up a lot on standardized tests. All right, let's look at this one, the transformer. We're going to do transformers, and we'll look at how they change or how they operate. But here, we just want to look at transformers in terms of their power input and output. Y'all know how the transformer works? Have you ever seen a transformer? No? Well, you know what a transformer is, right? What do they look like in your neighborhood?
Cars.
Huh? Cars? Or bugs sometimes.
What?
Yeah, they can be bugs too.
Oh yeah, those.
Yeah. You remember the transformer bugs? The insects? They transform into robots. Transformers, or meets the eye. Transformers, robots in disguise. Right? That's what you meant? Dude, I love those. Optimus Prime. I'm sorry, what were we talking about? Transformers. No, it's not a car. It's on your utility pole you have outside your house. There's like this big metal can on your utility pole. So we'll talk about transformers and how they work. It has to do with alternating current, and they generate a magnetic field, and then they generate another current. We'll talk about all of that later this semester. But what they do is they take an input voltage and they produce an output voltage that's either bigger or smaller. So like in your neighborhood, those lines up on the street, they carry a few thousand volts. But you don't need a few thousand volts coming into your home, right? You only need 120 volts. The reason they do that, by the way, the reason they have a few thousand volts is because it allows for the transmission of electricity with not much loss, right, to heat and what have you. So you can transmit electricity over very long distances without much loss. So those big lines that you see out going across Texas, those are like 30, 40, 50, even more thousands of volts. So those are very high voltage primary lines that bring electricity over long distances. But in your neighborhood, you're going from about 3,000 volts down to about 120 volts. 3,000 volts up here, and then 120 volts going down into your house. This is called a, when it goes smaller, this is called a step-down transformer. But in this case, we're looking at one that takes a larger, this is called not a step-down, but a step-up transformer. So it's taking a small voltage, Vin, and it's making it bigger, making it step up to V out. There's nothing going on in the transformer. It's a completely passive device. So that means that there's no energy going into the transformer. It's just a can. It's a can. It's filled with mineral oil mostly, and it has two coils of wire sitting next to one another. They don't even touch these coils of wire. Current comes in one coil, and then current comes out another coil. So with this step-up transformer, you must be asking yourself, where does that energy come from, right? If I'm increasing my input voltage by a factor of 3, by 300%, where the heck is that energy coming from? Aren't you asking yourself that question? No. Well, you should be asking yourself, because remember, voltage potential has a lot to do with energy. It's an energy per charge. But the difference here is that here I have a small voltage, but a big current. And here I have a big voltage, but I have a small current. All right, so it's not so much that you're increasing the power output of your electricity, but instead you're swapping back and forth between voltage and current. So those 3,000 volt lines outside your home, they have a very low current. But when it comes into your home, you have a much higher current. Here, when we're going from a small voltage to a big voltage, we have a big current, and then we have a small current. So what is the ratio of I out to I in? What is I out to I in? Is it A, 1 to 1? Is it B, 1 to 3? Is it C, 3 to 1? D, 1 to 9? Or E, 9 to 1? Which is it? The ratio of I out to I in. Think about our power expression.
What makes the transformers like blow up?
I don't know exactly. Does anybody know? I think. I, what makes the transformers blow up? And they get too hot? Okay. Yeah.
That's just one. I hear everyone saying, transformer blew up, we don't have power.
Right. So if you get like electricity, like a lightning bolt hits the transformer, that can cause it to explode because it gets too hot. Yeah, I guess if it leaks over time, the oil gets out. It just has mineral oil. It insulates the electricity and sort of keeps it cool. But I don't know exactly. Heat and degradation. All right. Let's stop at 115. 115. Let's see, 1 to 3. Yeah. So my output voltage is 3 times. It says V out to V in. This is equal to 3 to 1 because I get this 300% larger. And the I out to I in then is going to be 1 to 3. Let me write the equation. If you're not buying that with the ratios, our power is equal to V times I. For V out, I'm increasing V by a factor of 3. It's a step up transformer. I'm increasing the voltage by a factor of 3. In order to keep the power constant, I have to decrease the current also by a factor of 3, or by a third. So when I do this, big voltage, small current, then these cancel out. I'm still having the same power output. I don't have any extra energy coming in. I'm just sort of changing the voltage and the current in order to get this step up or this step down. Listen, we'll spend a whole section on that later as we get into AC electricity, but that's all I just want to talk about in terms of power here. We'll watch a video later too about how those things are made. It's pretty cool. All right, let's try these. Which light bulb in your house draws more current? Now, in your house, the voltage is constant. Everything in your house operates at the same voltage. You probably know it's what? It's 120, or sometimes we say it's 110. It's a difference in sort of how we think about AC electricity, but we'll say it's 120. So everything in your house, whether it's a 40 watt or a 100 watt bulb, operate at 120 volts. All right, let's stop at 1 minute. Okay, good. The 100 watt is right. P is equal to VI. This voltage is constant. It's constant. And so, if this goes up, this goes up. You can think about it in that way. Or you can think about it too that, light bulbs or any device, any electrical device, if it produces more energy, that energy at its very basic level comes from electrons. Those electrons move through a device and they take their electrical energy and they give it to the device in some way. For a light bulb, they give it in the form of light and heat from the light bulb. And so if I have something that gives off more energy, that means I must have more electrons. So my 100 watt bulb is going to have quite a bit larger current. In fact, 100 over 40 times the amount of current, 10 over 4, what's that? 2.5 times the current that a 40 watt light bulb has. We'll see some more questions like that later. Let's try this next one. Let's stop at 45. 45. I'll go on to 50. 50. Okay, good. So a couple ways you could do this. We know that power is equal to VI. All right, we know the voltage, but we don't know the current. We could find the current. We could say I is equal to V over R. Right, that's our Ohm's law. 150 over 50. That's equal to 3 amps. So it's going to be equal to 150 volts times 3 amps, or 450 watts. Another way, you could take one of those alternate expressions for power. Let's say P is equal to V squared over R. We have V, we have R, 150 volts squared divided by 50 ohms. That's also equal to 450 watts. All right, so 2 different ways you could do that. Either way is fine. How about what amount of energy is dissipated across that same resistor in 3 seconds? We already said it was 450 watts. Now, what amount of energy in joules is dissipated in 3 seconds? All right, let's stop at 55. Okay, good. B is right. Our energy, power is energy over time. So our energy then is power times time. We've already found that that's 450 watts times 3 seconds. That's equal to 1350 joules. All right, good. Let's see. Why did the boy eat his homework? He literally ate his homework. The teacher said it was a piece of cake. All right. That's the end of chapter 3. We are going to move on to chapter 4, though. I really don't see much distinction between chapter 3 and 4. Work through these homework problems. you're probably not going to see any problems exactly like the homework, but you'll see variations of it combined with other things that we do with circuits. So it's important that you work through them, but just don't think that you'll see problems exactly like these on the test. A lot of these we've worked sort of similar ones. There are only a few. Now we're going to do DC circuits. This is a pretty big chapter, and this will make up most of our tests next time. It'll sort of combine some of the ideas that we've seen in Chapter 3. If you're in the lab, many of you are in the lab, I know a few of you are not, but if in your lab, you've already done a lot of this chapter, but we'll see some parts that you haven't done yet. And in fact, the combination circuits we'll do to greater detail. We'll do more complicated circuits. So the first thing, this is actually a new idea. Even if you're in the lab, we haven't talked about this. A battery or a power supply is a source of what we call electromotive force. And we use this symbol. It's called EMF, or electromotive force. And the EMF, we use the script E. You know, we move electrons. We move charges. The batteries provide some way to move charges with a force. So that's why we call it an electromotive force, that our battery provides this difference in potential, like a charge rolling down a hill, that provides a difference in potential for those charges to gain energy. They give energy to our electrons and cause them to move. Batteries and power supplies also have an internal resistance. R, and this resistance causes a drop in voltage. So for example, in this battery, I have, the big gray thing is a battery, and inside the battery, I have this source of EMF. Now we've drawn our batteries like this before, but now we're assuming also that it has an internal resistance. So this is all part of the same battery. As this EMF drives electrons through the circuit, it generates a current, and we experience a drop in potential inside the battery. Like before the electrons ever get outside of the battery, they experience a drop in potential. So while you might have a 9-volt battery that ideally provides 9 volts, when you put it into a circuit, you might only get like 8.5 volts because you're losing a half a volt of energy inside the battery itself. In fact, what happens to a resistor when you heat it, when you run electricity through it? Well, it gets hot, right? Some of y'all have seen that in lab. If you run too much current through a resistor, it'll get hot, and sometimes it'll even fizzle up and burn. But if you put too much electricity through a resistor, then it gets hot. And the more and more resistance you have, it'll get hotter and hotter as you run more and more electricity through it. That's why when batteries, like on your cell phone, when they start to go out, what happens to them? Huh? They get hot, right. That's because their internal resistance, as the chemicals degrade inside that battery, their internal resistance begins to increase. Ideally in your battery, you want no resistance at all because you're losing energy inside of your battery before the electrons ever get out at all. So in this case, our terminal voltage, that's this voltage, delta V, is equal to the EMF minus the voltage across the internal resistance. This comes from Ohm's law. Remember we saw Ohm's law before. V is equal to IR. And so this then represents the drop across the internal resistance, the drop in potential across the internal resistance. All right? Let's try this. Have y'all ever, I know some of y'all might have had old cars, like 1980s and before. In cars, they used to put voltmeters in the cars. You ever see a voltmeter in a car, like on the dashboard? Josh, you seen it? 70s vehicles, maybe 80s. When I was a kid, like the big thing was actually put a voltmeter, like aftermarket, on this column. But when you're running your car and you see the voltmeter, it tells you the voltage that you're getting out of your electrical system. When you turn on something like your air conditioner or your heater or whatever, or usually your air conditioner, the voltage drops, right? Because you have this internal resistance you have this internal resistance, and when you add devices that draw a lot of current, they take away from your potential in your electrical system. They actually take away some of your energy, the more and more current you have. You might see this in your house too. You shouldn't see this, but sometimes in your home, if you turn on something that takes a lot of current, you'll see a slight dimming of the lights. Usually in older houses, our house does this. It shouldn't happen this way because you shouldn't have very little resistance in your circuit. But sometimes when you turn on, say, a bathroom heater in your bathroom, if they're on the same circuit, the light will also dim just a little bit. It's a similar reason because of this internal resistance. I'm increasing I, and so I'm decreasing the voltage. All right, let's try this quick test. My battery consists of an EMF source, 12 volts. However, when I have 4 amps coming out of the battery, I really only get 10 volts. What is the internal resistance? All right, y'all doing awesome on this. This is good. I'm going to stop here in just a moment. I'll stop at, say, 102, just 5 more seconds. All right, good. B is right. The way I do this is I say delta V. That's my terminal voltage, or the actual potential difference that I get, is equal to the EMF minus I times my internal resistance. So I get 10 equals 12 minus the current, which is 4 times R, and I solve that for R. It's negative 2 over 4, or 0.5 ohms. You want your internal resistance to be as small as possible. And in this case, we have about a half an ohm. But notice that I get quite a bit of a drop. I go from 12 volts, which is what I would get if I had no internal resistance, down to 10 volts off of my battery. All right, let's look at this circuit. We're going to introduce now the idea of the loop rule, and this will be very important. It's a very important rule that electrical engineers and electricians use when they're analyzing circuits, and we'll use it a lot too. I like to think of a circuit as a roller coaster. You ever been on a roller coaster? You get on a roller coaster and you get in the car, and what do they do right away? Right, you climb up to the top of the hill, and then you zoom down and you do all your business throughout the roller coaster, and then you'll lose energy because you have friction, and then you go, they pull you up another hill, right? Have you been on a roller coaster before? Did I tell you all the story about the roller coaster, my son, my daughter? I haven't told y'all that? You want to hear for just a second? I know you have lots of other things to do, but let me tell you. So we went to Six Flags. I told y'all this Six Flags story. And my wife loves roller coasters. I can give or take. I never saw a roller coaster when I was a kid. Mississippi, we don't have roller coasters. But my wife loves roller coasters. She lived right next door to Worlds of Fun in Kansas City, and she would go there in the summer and ride the roller coasters. And so she was really excited when we went to Six Flags last summer in St. Louis. And she's like, I'm going to take the kids on a roller coaster. I'm like, I don't know, I'm not sure they're going to like it. But so we get to Six Flags. We were the first ones in, and we went straight to the back of the park and rode the Screaming Eagle. This roller coaster. It wasn't like one of the big ones that goes upside down, but it was a fast roller coaster. It was like an old wood roller coaster. And they get on there, they're all excited because they don't know what it's going to be. And then we start going up the hill, and they both wanted off the roller coaster. My son started crying, my daughter was just, oh. And then we got off the roller coaster, and Kaz was like, let's go on another one. No, we don't want another one. But we did trick them a little later. We went on another roller coaster, but we didn't call it a roller coaster. We called it a train. Let's go on the train. And so they said, later we said, oh, did you realize that was a roller coaster? Like, yeah, we knew it was a roller coaster. But we felt like we were putting one over on them. That's bad parenting, like to trick your children into things they don't want to do, but it worked for us at the time. So I like to think of these as a roller coaster. And your roller coaster, your car, is here, and it comes up along the way, and then you chug up that hill, and then as you go along, you gain a lot of energy when you go through the battery, and then as you go along, you lose a little bit of energy as you go through the resistor, and then when you go through the other resistor, you lose a little more energy until you come back to the battery. So as I'm going through the circuit, I gain energy right here, I lose energy, I do a loop-de-loop or whatever, I come up here, I lose a little more energy, I do another loop, and then I come back and I have no energy at all. I've lost all the energy that I've gained from that battery, and then I do the whole thing again. I gain energy, and I go through and I lose it. So the component that they gain energy is the battery, or the power supply, whatever your source of EMF is. And then in the resistors, they lose the energy. So we can think of a positive potential right here and a negative potential here, or a negative change in potential, and that's going to be equal to my negative I times R. All that energy will go into, mechanical or thermal energy usually. With resistors, it's usually thermal energy. But you can do various things with circuits to convert it to mechanical energy. And we'll talk about that when we get into magnetic fields, because it has a lot to do with magnetic fields to actually provide a force. So each component either gives a drop or a rise. Our delta V for the EMF is equal to positive E. You get a rise in potential. Our delta V for my internal resistance is equal to minus IR. And then delta V for the big resistor, that's like out in the circuit, is equal to I times R negative IR. And when you go around the circuit, the change in the potential is 0. Whatever energy I had at the beginning, that is 0 energy. When I come back to that same point, I still have 0 energy. All that energy is lost in the circuit. So an electron at a particular spot in a circuit will have the same energy when it returns back to that spot. And remember, we're talking about it in terms of energy, but really we're talking about energy per charge or voltage. So now we can come up with the loop rule. The loop rule says that the sum of the potentials across a closed loop, that's to be closed, that is you start and finish at the same point, is equal to 0. So in this case, I would have positive EMF minus the potential across the resistor minus the potential across the second resistor. That's all equal to 0. That's the loop rule for that particular circuit. We're going to use the loop rule a lot. We'll use it as we deal with combination circuits, and then we'll also use it with multi-loop circuits. If you did the Wheatstone bridge, you saw the loop rule. My lab, we skipped Wheatstone because we did something else. But if you did the Wheatstone bridge in lab, you saw the loop rule. And then we'd solve for the EMF. The EMF in this case then would be IR plus IR. All right. So that will get us up to resistors in series. I think we'll stop there. I want to hand out your test.